Okay, so now let's go to Webster 4. This is three articles I wrote for Baseline, again about 11 years ago, on metrics. Metrics are a sore point within software engineering. They represent an effort to try and gather information about what the state of the project is, usually in hopes of being able to more accurately predict when it's going to end. Sometimes in hopes of trying to judge the productivity of individual developers. I can tell you right now that for most organizations, the metrics they collect are useless at best and counterproductive at worst. They measure the wrong thing. They don't really tell you where things stand in terms of project progress. I mean, the most common metric of all time is lines of code, which makes absolutely no sense, particularly if you understand refactoring, where you engineer and end up with less code. The idea of, we're breaking out, 100 lines of production quality code a day. That tells you absolutely nothing about how close you are to actually having a working finished product. Yeah?
Isn't the follow-up to lines of code being a bad metric that it's better than most of them?
No, it's not. It's actually, I think, particularly with the advent of object-oriented development, it's worse than most of them. I think, it can tell you some things, but I'm not sure it really tells you anything meaningful about what we're going to see in the next slide. Why lines of code is popular is because it does, unlike a lot of other metrics, it does have the three important qualities. First, it doesn't have informative predictive. That part it lacks. But it is automated and it is objective. In other words, it's not someone saying, well, I judge this to be 80% done. You run a tool, a shell tool. Bam, here's how many lines of code there are. And with some environments like, okay, here's the number of files, here's the number of objects, here's the number of check-ins we've had, so on and so forth. A good metric has to be automated because if it has to be done by human factors, by human judgment or evaluation, it's not only not objective, but people get tired of doing it. So you really want something you can press a button. That's why lines of code is so popular. The problem is lines of code is almost never predictive as to how close you are to being finished or how much progress you've made. Other than, I have 0 lines of code, I have 10 lines of code, I have 20 lines of code. Okay, yeah, you're obviously not making a lot of progress on that, except, and getting back to flow and productivity. When I was at Monitor Labs, I was chief. What was my title there? I was basically head of programming there, which it was me and Guy Grotke, so it's not a big team. Monitor Labs built data acquisition devices. These were little boxes that would sit on smokestacks and measure the emissions, and then transmit that information back, so that industrial facilities could gauge their actual emissions and see if they were meeting EPA standards, and if there were things that were starting to spew out that shouldn't be spewing out, kind of like Sandy and the water problem for the last few days. You get early detection of that. Well, Monitor was going to do this whole new line of data acquisition units, Tabasco line, and I was responsible for coming up with software architecture for it. At this point, I'd already been working there for, I guess, at least a good 3 or 4 months. I had done patchwork and bug correction and feature addition to some of their software for the existing devices. Most of the existing devices, it was not only all assembly languages, it was obscure assembly language. Things like Fairchild F8, where you have like a memory space of 256 bytes to work with, things like that. And Guy Grotke and I had hashed this over, decided we were going to use Forth. This was 6502 based series of devices. It's the same microprocessor that was in the Apple II. And There were some good Forth implementations for it, and Forth has the advantage of being very tight and compact. So we wanted to go that way instead of just assembly code. But I had to come up with the architecture, software architecture. And I had an office and I had a desk. And for 3 weeks, I sat at my desk with my feet up on my desk staring at the ceiling. Now, I had been hired by Steve Goldberg, who was the VP of Engineering, one of the founders of the company. Bright, wonderful guy, one of the best people I ever worked for. But I actually, in terms of line management between me and the CEO, I had a non-technical manager over me. And he knew I was supposed to be working in the architecture, and he'd walk by my office like twice a day in the hallway, and he'd glare at me. Because all I was doing is I was literally, sitting out in my chair, leaning back, feet up on the desk, staring at, it was, acoustic ceiling like this. But mentally, I was sitting there thinking through everything I needed to know. And everything that the software was going to have to do. I was looking at various approaches, we can do this, we can do that, well, this will cause this problem. I was doing a lot of that exploration that Arnold talks about. And this manager was getting more and more frustrated with me because, we have a schedule and a time pressure and everything else, and by any measurable metric, nothing was happening in 3 weeks. And finally, after 3 weeks, one day I thought, okay, I know what I'm doing. And I put my feet down, and I pulled out a pad of graph paper, and I started basically documenting the whole architecture, and that's what we built. And we built it successfully, and the architecture was great. So the problem with metrics is that they don't always measure what's essential. Most major metrics lack one or more of these attributes. That is, they're not informative or predictive, or they're not objective, or they're not automated. And here's why it's, laws of metrics. Yes, we've talked about some of these. Jerry Weinberg, his law of metrics. That which gets measured gets fudged. This is the bug bounty issue that I talked about. If your metric is lines of code, you know what people are going to do? They're going to run a lot of lines of code. They may even change their formatting to increase the number of lines of code. Well, let's see, we're going to introduce a blank line. Oh, well, we'll take out that thing. Well, I'm going to introduce a extra set of braces for every block. That which gets measured gets fudged. We've already talked about the 90% rule. Metric law of least resistance. The more human effort required to calculate a metric, the less often and less accurately it will be calculated. In other words, if you're using a metric that requires someone to sit down and look at the code and document stuff in effect by hand, it's going to get abandoned. Or it's going to get sloppy. Maybe you have someone who's assigned full-time to do this. They're kind of like, yeah, sort of that. It just becomes tedious. Now, there's an important book, and I recommend that you remember this if you find yourself in a situation where you're in an organization that's trying to do management by metrics. Robert Austin wrote this horribly underappreciated and unknown book back in '96 on measuring and managing performance by organizations, in which he very, very methodically and really from a sense of logic and philosophy documents everything that goes wrong with trying to manage employees using metrics. What a distorting impact it has on the organization, and why it almost never works. In fact, it tends to be counterproductive. If you're looking for a book for extra credit reading, it's not a terribly thick book. It's one that I would recommend. Now, why are software project metrics so hard? It's because of armor again. Here's the situation you have for a project under development. You started it, you're at some point, and you're trying to say, when are we going to be done? The problem is all the things you don't know yet. It's your levels of ignorance. How much analysis are you going to have to do? In other words, is there information you still have to gather that you haven't gathered yet, and you may not know that you haven't, that you need to gather it and that you haven't gathered it yet? How much invention, how much problem solving do you still have left? And do you know everything that you're going to have to solve? Is the current architecture, design and implementation adequate for the solution? What happens if you get the, your current implementation done and you find it's too slow? One of the projects I consulted on was for a financial company that offered credit cards, and they were still using software from a bank they had bought up. That's how they got into the credit card business. They bought up a bank that was doing credit card. It was running on old mainframes in mainframe assembly language, and that's where they did all their credit card transaction processing. So their goal, and this is about roughly 20 years ago, their goal was to rewrite all this. We're going to use distributed objects, Corba. How many of you have ever heard of Corba? Oh, someone has. It was one of those marvelous things that came and went. Never really fulfilled its promise. So they're going to use this distributed objects on Unix workstations, and part of what they were doing is they were bringing this data over from the mainframe and then doing the processing on these Unix workstations. Well, the problem was, how many of you know what EBCDIC is? Found one. EBCDIC was basically the equivalent of ASCII for mainframes 50 years ago. Extended binary character something, something, something. It's what ASCII replaced in computing. So it's a different character encoding thing. Well, the data, all the financial data on the mainframes was in EBCDIC. But of course, all the software running on the Unix system is going to run it's all going to be ASCII. It's going to expect ASCII characters. So, some bright engineer, this finance company, had written a distributed object service that would convert the data coming over from the mainframe from EBCDIC to ASCII. The problem was, it was 1,000 times too slow. Their window for processing transaction was 2 hours each night. In other words, you have to, basically, they would for 2 hours each night, they'd have to process all the credit card transactions that came in. And they were literally 1,000 times too slow to process the amount of data that they had coming in. Their solution was not feasible. Now, in this particular case, we had one of our senior, the company I was working with, OSG, we had one of our senior architects come in to review these problems, and this was the first thing, and he just sort of shook his head. Because they had this whole complex Corba-based distributed object system to do the EBCDIC to ASCII conversion. He wrote a 10-line program in C that used a lookup table that was 100 times faster. He said, okay, I've gotten rid of 2 of your 3 orders of magnitude. Now you're only 10 times too slow instead of 1,000. He said, we'll have to find other things to change to get this within the appropriate speed. By the way, the project ultimately was canceled. The amount of coding that actually still has to occur, that's hard to predict. And there are estimates, there are all sorts of models that try to produce this. Stuff like Kokomo 2, and you've got function point estimates, and so on and so forth. But when you start to mix in the issues of incomplete analysis, incomplete invention, incomplete discovery, it becomes very hard to predict how much code you have to do. Then you've got the question of how much testing, how much quality engineering, testing, reviews, so on and so forth, you're going to have to do to make sure this actually works properly. What happens if you do get it all and it's working correctly, but it is, in fact, not 1,000 times too slow, but what if it's just 50% too slow? What can you do to make that up? Yeah? Build it, yes. Say, start over. Rethink what you're doing. unexpected turnover among engineering personnel, changes in market requirements. Number one cause of startup failure is lack of market demand. We're going to build this, and by golly, we're going to get, we're going to be rich. This app is going to get picked up. We're going to be on the most favorite list on, the iTunes store or the App Store. And we're going to make a bundle, and you push it out there, and literally no one buys it. That's very easy for that to happen. You'd be surprised. Changes in external systems on which you depend. This can be the operating systems. This can be libraries. It can be external APIs, external services, so on and so forth. These are all the reasons why it's hard to predict when a project's going to be done. And management has a hard time seeing most of these. They just have a hard time grasping the level of uncertainty there is with software. Part of the problem here, concrete doesn't change in formulation every 18 months. Concrete is, there are some tweaks here and there, but concrete is basically concrete. Steel is basically steel. But stop and think of the turnover in technology in terms of the operating system platforms. I have apps on my iPhone. Like I suspect most of you, I have probably about at least 10, maybe 20 apps on my own iPhone for every one that I actually use. And every now and then I toy with, I should just delete a lot of these. And then another part of me says, no, because you might use it at some point. But I've had ones which I've thought, oh, I haven't used that for a while, and I go to launch it, and I get the little message that says, I'm sorry, this doesn't work in iOS 12. In fact, it probably didn't work in iOS 11 and iOS 10 either. So you can have the operating system change out from under you. You have APIs that can change. So what do? Well, this is very interesting because this was a thought I had back in 2008. I said, well, here's what triggered this. My very first job out of college was at General Dynamics, and I worked on several projects there. One of the projects was an effort to try and distinguish between real tanks and fake tanks. At this point, the Soviet Union occupied Eastern Europe behind what was called the Iron Curtain. And they had military forces stationed all along that border. And of course, we had spy planes and satellites that would go over and photograph them because we wanted to know where these tanks were. Well, what the Soviets then started doing is they built these nicely painted, very effective plywood tank shells and put them on top of trucks. And from a high altitude top-down look, you really couldn't distinguish which were tanks and which were trucks. So you had a bunch of real tanks and a bunch of fake tanks, and they'd keep moving them around. And we couldn't tell where they really had tanks and where they simply had these fake tanks. So this engineer I worked with at General Dynamics had an idea to use side-looking radar, basically helicopters that would be like 20 miles from the Iron Curtain, and would bounce radar signals off of these vehicles to try and tell if they were tanks or trucks. And the way they did that was that you'd have the radar signal. He hypothesized that there were radar signal differences between something coming back from a vehicle with wheels or a vehicle with treads. And he went out to Camp Pendleton, Marine Camp there in San Diego, gathered data, and then I wrote a program that did basically Bayesian analysis. We had 26 characteristics off a radar signal, and we found that with just 3 characteristics, we could get 95% separation. So in real time, and just using 3 characteristics of the radar signal coming back, the helicopter can look and say, tank, truck, tank, truck, tank, truck. Well, the thought I had was, why not apply to software projects? Rather than try and have these predictive, de facto metrics, why not actually instrument a software project? So you're gathering all sorts of data about it. And then at the end of the project, try to correlate the data with the actual project performance. And see which characteristics were most predictive of either problems or success on the project. This was sort of, here's an idea, here's something to throw out. Towards the end of the semester last semester, I had one of my students here who had read these things, said, Brother Webster, I found a company that I think that's doing what you're talking about. It's a company out of Colorado called Get Prime. You may have actually seen they've had billboards on I-15. Some of you may have seen those. And I went and looked at their website and said, oh my gosh, they are. This is exactly what I talked about doing. And actually met at the Silicon Slopes Tech Summit. I had about a 45-minute meeting with their CEO, just sort of to share ideas and so on and so forth. And I said, I'm so thrilled. And apparently a lot of it is very effective. They have a whole set of instrumentation tools. Basically, their software locks in to GitHub and various other development tools and utilities, and they simply monitor them constantly, and then they do after-the-fact analysis to find out what is most predictive of either problems or progress on a project. They have some great white papers there. Here's something interesting, which made a lot of sense once he explained to me. I asked him about some of the analysis. He said, here's one that's interesting. He says, they talk about this difference in talent and productivity. They said, yeah, we can see up to a 10-to-1 difference between individual developers. He says, but here's what's most interesting. Once you get a large enough team, even for the most talented developers, productivity tends to sink down to the level of everyone else. In other words, after a certain team size, the constraining factor of the productivity of the whole team tends to have to deal with the productivity, the general or the average productivity of the team, rather than any one individual developer. Because that individual developer really can't get that far ahead of everyone else. She or he has to depend on what other people are doing and interact with other people. Yeah.
What are the heuristics that they're looking at to hypothesize that?
You'd have to go look at their website. So they've got they do a lot of data analysis. They've got a lot of white papers out there. If you're interested in looking at this, I'd go out there. But they spend time looking. I still want to get up to speed with this and get an account, and I've talked with them about that. So I don't know a whole lot more other than some of these conversations I've had with them. So that's the end of that lecture. Hang on.